This section deals with how to multiply together two or more polynomials. What we're going to do is we're going to use some things that we already know about how the basic math operation of multiplication works. And we're going to use that to multiply together expressions that have lots of different degree terms. So the things that we multiply together will have some first degree terms, some second degree terms, that is things where the variable is squared. We may have some third degree terms, etc. First, let's think about what we already know about what multiplication means. If I were to ask you to show me a picture of the multiplication problem 3 times 5, one thing you might do is to draw something that looks like this. You would draw me a rectangle that had a width of 3 and a height of 5. And if you did that, your rectangle might look like this. It's 3 squares wide and 5 squares tall. And the total area of this rectangle is 15, because 3 times 5 is 15. We call this the area model of multiplication. Similarly, if I asked you to show me a picture of 2 squared, you would show me a square that is 2 units wide and 2 units tall. It would be a square because its length and its width are the same. And the area would be 4. 4 is what we get when we take 2 and square it, when we make a square that's 2 units on each side. Now this works nice and neatly when we're multiplying together our constants, that is, plain old numbers whose value don't change. But we can extend this idea to thinking about multiplying variables. For example, if I asked you to show me a picture of what 2 times x looks like, we could draw a rectangle that was 2 units wide and x units tall. And obviously I don't know how tall to make x exactly because x is a variable, but I can still represent it with a line of a certain length. If I show a rectangle then that's 2 units wide and x units tall, it would look like this. It would have 2 blocks. Each block is 1 unit wide and x units tall. So the area of this would be 2x. 2 times x is 2x. If I asked you to show me a picture of x squared, I would simply make a square that has both a length and a width of x. The area of this square then would be x squared. It would be x times x. We can extend this idea even further to show what happens when we multiply a constant by an expression. In this case, we're going to multiply the constant 2 by the expression x plus 1. So we're going to make a rectangle that's 2 units wide and x plus 1 units tall. Notice that in this case I showed the height of this rectangle in 2 separate chunks, a chunk that's x units tall and another chunk that's 1 unit tall added on to that. If we look at the areas that result when we do this multiplication, the first chunk is a rectangle that's 2 units wide and x units tall. It has an area of 2x. The second chunk is a rectangle that's 2 units wide and 1 unit tall. It has an area of 2 times 1, or 2. When we add these together, the total area of the blue rectangle is 2x plus 2. That's what we get when we multiply together 2 times x plus 1. We can extend this even further to show what happens when we multiply 2 binomials together. In this case, we're going to multiply x plus 1 times x plus 2. So we'll simply make a rectangle that has a width of x plus 2 and a height of x plus 1. Now if you look ahead a little bit, you may realize that this is going to give us 4 rectangles inside. Let's look at them one at a time. The first rectangle, shown here, has a length and width of x. So the area of that rectangle is x squared. The next rectangle has a width of 2 and a height of x. So its area is 2x. The third rectangle has a width of x and a height of 1. So its area is 1x, or just plain old x. And the last rectangle has a width of 2 and a height of 1. so its area is simply 2 times 1, or 2. So if we add together the area of all 4 of these rectangles, we would get x squared plus 2x plus 1x plus 2. We can do a little bit of combining of like terms here, and when we do that, we see that the total area is x squared plus 3x plus 2. What this means is that when we multiply together the binomials x plus 1 and x plus 2, what we get, the result, is a trinomial. It has 3 terms. The first is x squared, the second is 3x, and the last is 2. What I'd like you to do now is to pause this presentation and you draw the area model to show how to multiply the products below. So first, draw a picture that shows what 2 times the quantity x plus 3 would be, and make sure you label each of the parts in your area model. Then, draw a picture that shows what x times x plus 3 would look like. And finally, draw a picture that shows what x plus 1 times x plus 3 looks like. Again, make sure you label each of the rectangles in your area model. When you're done, you're going to resume this presentation to check in the work, see if the work that you've done is correct. All right, so you've drawn some rectangles and you've labeled the area of each of them. Can you connect in the drawings you made? Can you show me how the area of the first rectangle that you drew is 2x plus 6? And the area of the second one that you drew is x squared plus 3x? And the area of the third one that you drew is x squared plus 4x plus 3? If you can, that's excellent. Congratulate yourself. If not, you should go back and either note where you got confused or a question to ask during class. Your book shows a slightly different process for multiplying together a monomial and a polynomial, and I want to connect that to you with what we've been doing with this idea of multiplication as a way of showing area. So here's an example from your textbook. It asks you to find the product between 2x cubed, that's a monomial, it has one term, and x cubed plus 3x squared minus 2x plus 5. In this case, this is a polynomial with 4 terms. So we're going to multiply together this monomial and an extended polynomial. What we can do is we can apply the distributive property. We have the 2x cubed on the outside of the parentheses being multiplied by each term on the inside of the parentheses. When we do that, we see that first we have 2x cubed times x cubed. Then we have 2x cubed times 3x squared. Then we have 2x cubed times negative 2x. Then we have 2x cubed times positive 5. When we use the rules of exponents to simplify each of these terms, the first term becomes 2x to the 6th, the second one becomes 6x to the 5th, the third is minus 4x to the 4th, and the last term is 10x cubed. How does this connect with what we've been doing using an area model of multiplication? Well, imagine that we made a rectangle that was x cubed plus 3x squared minus 2x plus 5 units wide and 2x cubed units tall. And then we found the area of each of the rectangles within this. We would see that the math we're doing is really no different than applying the distributive property up above. And what it results in is the same sum of 4 terms. Your book also shows a method called multiplying polynomials using a table. And this is really very similar to what we've done with an area model of multiplication. So for example, the book suggests that if you're going to multiply together x minus 4 and 3x plus 2, that you take the following steps. First, change any subtraction to plus a negative in each polynomial. This will help us keep track of the signs in our problem. So we're going to change x minus 4 to x plus negative 4. I do recommend this as it helps you make sure that the negative signs stay associated with the correct terms. Then we're going to write x plus negative 4 and 3x plus 2 along the sides of a table. So down the left-hand side of this table is x minus 4, and across the top of this table is 3x and positive 2. You can see a connection here between what we did with our area model and this idea of using a table for the products. Then we multiply the row and column headings for each element in the table. So the first square in the table is 3x times x. That gives us 3x squared. The next square in the table is going to be 2 times x, which gives us 2x. And on till we filled out the squares in the table. Lastly, we need to add together the products in all 4 squares of the table. So we add 3x plus 2x minus 12x minus 8. And then we combine like terms. In this case, we have 2 first-degree terms. We have 2x and negative 12x. When we combine those, we get negative 10x. Now, you try. Let's find the product of a plus 3 and 2a plus 1 using a table. Please pause this presentation and resume when you think you've got it. All right, so let's see what we've got. If we make a table of the products, we'll have a and positive 3 down the side, and 2a and positive 1 across the top. Notice that it doesn't matter which polynomial you put across the top and which you put down the side. It does matter that you keep the parts of each polynomial correctly together. For example, a plus 3 is one of the polynomials we're multiplying, and so a and 3 either have to both be down the side or both be across the top. When we make this table of products, we see that what we get is 2a squared plus a plus 6a plus 3. And then we combine the like terms, the a and the 6a, together those make 7a, to get 2a squared plus 7a plus 3. Another way that we can do this is multiplying polynomials horizontally. That means from side to side. And this really works best when what we're multiplying together are 2 binomials. For example, 2x plus 3, that's a binomial because it has 2 terms. The first is 2x and the second is 3. And 4x plus 1, that's a binomial because it has 2 terms, 4x and positive 1. Here's the trick, and it really is only a memory trick, for how we're going to multiply these together. We multiply the first terms together. This is shown with the red arrow here, so 2x times 4x. That's multiplying the first 2 terms together. And then we're going to multiply the outer terms together. So that is 2x and positive 1. These are like the outside terms in the way this is written. Then we're going to multiply the inside terms, the 3 and the 4x. That's shown with the black arrow underneath this expression. And finally, we're going to multiply the last 2 terms, 3 and 1. That's shown with the blue arrow here. There's a lot of arrows flying around all over the place. So here's a little acronym to help you remember this. What we're doing is we're multiplying the first terms together. 2x times 4x, that gives us 8x squared. Then the outer terms together, 2x times positive 1 gives us 2x. Then the inner terms together, 3 times 4x gives us 12x. And then the last terms together, 3 times 1 is 3. If you look at this sequence, first, outer, inner, last, it spells out the word FOIL, F-O-I-L. We're going to be doing this kind of multiplication a lot, and FOIL is kind of a nice shortcut to help us. It only works when we're multiplying together 2 binomials, that is, 2 things that each have 2 terms. So let's practice multiplying some binomials using this FOIL pattern. Please pause for a minute while you use FOIL to find the product of 3a plus 4 and a minus 2. All right, let's see how you did. Multiply the first terms together, 3a times a. Multiply the outer terms together, 3a times negative 2. Multiply the inner terms together, 4 times a. Multiply the last terms together, 4 times negative 2. Now we're going to simplify each of these terms. 3a times a is 3a squared. 3a times negative 2 is negative 6a. 4 times a is 4a. And 4 times negative 2 is negative 8. Next, we're going to combine like terms. In the middle, we have two terms that have a as their variable. The first is negative 6a and the second is 4a. When we combine those, we get negative 2a. So the total product is 3a squared minus 2a minus 8. Let's have you practice one more time multiplying these binomials out using FOIL. Pause this presentation and resume it when you think you have them correctly multiplied out. All right, let's see what you've got. Your first term should be 2x times x, that's 2x squared. Your outer terms should be 2x times 2, that's 4x. Your inner terms should be negative 5 times x, that's negative 5x. And your last terms should be negative 5 times 2, that's negative 10. When you combine the outer and inner, the OI in FOIL, you should get 2x squared minus 1x minus 10. So at this point, it looks like we've learned three totally different ways to multiply together some binomials. Let's see if we can't connect the table method, the FOIL method, and the area model with each other. Let's start with x plus 2 times x plus 2. If we use the table method, we would see that x times x gives us x squared. X times 2 gives us 2x. 2 times x gives us 2x. And 2 times 2 gives us 4. If we add these terms together, we get x squared plus 2x plus 2x plus 4. And notice where each of those terms came from in the table, which gives us x squared plus 4x plus 4 when we combine like terms. Now let's do the same problem using FOIL. When we multiply the first terms together, x times x, that gives us the f in FOIL, which is the x squared term. Notice where you see that same term in the table at the left. When we multiply the outer terms together, x times 2, that gives us the O in FOIL. That gives us 2x. When we multiply the inner terms together, 2 times x, that gives us the I in FOIL. That also happens to give us 2x in this case. Notice how the 2x plus 2x in FOIL corresponds to the 2x plus 2x from the table. And last, 2 times 2, that's our last term. That's the L in FOIL. That gives us the plus 4. So using FOIL and using the table give us the same sequence of the same terms when we multiply out. Finally, let's make a connection to the area model. If we drew a square in this case, because our length and width are the same, that was x plus 2 units wide and x plus 2 units tall, it would have 4 squares within it. The first is an x by x square. The second is a rectangle that's 2 units tall and x units wide. That's 2 x's. The next is 2 units wide and x units tall. That's another 2 x's. And the last is a 2 by 2 square that is an area of 4. So you can see the connection between the area model, FOIL, and the table. Now what I'd like for you to do is to repeat the process from the previous slide, only show the connection in this case between x plus 2 and x plus 3. These are slightly different binomials. So draw out the table, show the FOIL method, and draw out the area model. I'm not going to show you the answers to these during the presentation, but we will go over them in class.